Swayam Prabha. Digital India. Educated India.
So, in this lecture, I will discuss how to use those equations, those are derived in the previous lectures, to get the soil properties by using different or number of example problems. So, first example problem, it is given that the result of a refraction survey or test at a site are given as follows. I mean, at a site, refraction survey is done and you will get this data. These are the final data. So, that means as I know that we know the position of the geophone or the receiver. Here the distance from the source to the receiver, these are given 2.5 meter to 5 meter, 7.5 meter to 50 meter, and corresponding fast arrival time of the wave, because this is the advantage that here we will not, like seismic reflection test, we will not get the arrival time of two waves, direct wave and the reflected wave. Here whether it is a direct wave or the refracted wave automatically it will come, but we will measure the fast arrival time of the wave, and that is millisecond. So, determine the thickness of the layers and the wave velocity. Okay, that we have to do. So, now I have drawn these points in a graph. So, that is x axis is distance from the source in meter and y axis is fast arrival time, which is in millisecond. So, from where these data I have used and I have drawn. So, if you look at this graph, so here you will find there is a 3 distinct change of slope in the plot. So, I will join these points. Okay. So, I will join these points. So, you can extend them, it is not an issue, but actually these are the lines. So, I will join them. So, similarly, I will join them. So, or I will join these points. And then I will extend these points also. I will extend these points. Okay, I will join them and I will extend them. So, now these are the 3 lines. These plots I have, these data I have plotted, and then you can see 3 different slopes can easily be identified. So, now here you know that the first one will give me VP1, second one give me VP2, and the third one will give me 1 by VP3. Now, I will get the slope and that will give me 1 by VP1. Okay. So, from there I will get the VP1. So, the VP1 I will get from the plot is VP1, that is coming 490 meter per second. Now, if you plot them, you will get slight variation. Okay, but because that depends on how you are drawing these straight lines, so it will give you slight variations. Okay, but it will be roughly around 490 or 500 or 480 meter per second. So, or it is depending upon how you are plotting them. So, it will be 500 meter per second. Similarly, VP2 I will get the slope of second state portion of the curve, and that is giving me 1500 meter per second, or if you draw it in different way, it will give me 1467 meter per second. And VP3 is giving me 3600 meter per second. Velocity of this velocity of wave in the third layer. Okay, so now I have to determine 3-layer case. So H1, H2 I can determine because the thickness of the layer will be n number of layer minus 1. So here the 3-layer velocity I can determine for 3 layers, so thickness I can determine for 2 layers, 1 less. So here if I extend, this is my T01, this is T02. Now from here I will get that I am getting that T01 is 10 millisecond. That means 10 into 10 to the power minus 3 second. And T02, you can see this is 20 millisecond. 20 millisecond, which is 20 into 10 to the power minus 3 second. Okay. So now if I use the expression of H1, then I will get, I know that T01, that will be T01 divided by VP1 VP2 root over VP2 square by minus VP1 square. Okay, so now we'll put these values. T01 is 10 into 10 to the power minus 3 divided by 2 into VP1, let's say 500, VP2 is 1467, you can take 1500 also, but I am here, I am taking 1467 and root over 1467 square minus 500 square. So these expression I have already given in my previous lecture. I have to get the H1. But remember that I am using time intercept method, but you can use the critical distance concept also. But anyone is okay to determine this thickness of the different layers. So I will get this value H1 is equal to your 2.66 meter. So thickness of the first layer is 2.66 meter and velocity of the first layer is 500 meter per second. Now I will get the Z2 or H2 I will get T02 expression is T02 expression is 2 into H1 root over VP3 square minus VP1 square divided by VP3 into VP1 plus 2H2 root over VP3 square minus VP2 square divided by VP3 and VP2. So now I am putting all those values. So I will get T02 is 20 into 10 to the power minus 3. Just a minute. The expression that I have given is not. Yeah. So this is T0. Yeah, that is the expression here. That is okay. So this will be T02. Here the H1 expression is given. So from here also I can get actually how this equation is coming. It is T01 divided by 2H1 into 2 T01, that is your 2H1 into root over Vp2 minus Vp1 square divided by Vp2 Vp1. So this is actually T01. From here directly you will get the H1 expression. Either you put it here or you will get the H1, or you can get the put the T01 in the directly in the H1 expression, you will get the same result. So here I am putting here 2 into H1 is 2.66. Then this is Vp1. Vp3 is how much? 3600 whole square minus 500 whole square divided by 3600 into 500 plus 2H2. So this will be 2H2, then root over Vp3 is 3600 whole square minus Vp2 1467 whole square divided by 3600 into 1467. Okay, so from here I will get the value of H2 as 7.6 meter. So I will get all the required values. I will get the Vp1, Vp2, Vp3 and the thickness of first layer and the second layer. Now what soil parameter I will get? So you know that there are expressions are available. So you will get, you know that G is equal to rho Vs square. So if you measure the shear wave velocity in my lectures, I will discuss how we will generate the P wave and the shear wave, and then if you measure the shear wave velocity, then you will get the shear modulus by using this expression. Rho is the density. I have given this expression in my module 1. Similarly, or if you measure the Vp, then also if you know the Poisson ratio, you will get the shear modulus. Okay, so ultimately if you measure the Vs, directly you will get the shear modulus by if you know the density of the soil layer, and if you measure Vp, then you have to know the Poisson ratio of that layer, then you will get the shear modulus of that layer. So ultimately I will get the shear modulus of that soil from the velocity by using the available expressions. Okay, so this is my example 1. Or the next example, that between 2 points A and B, 2 seismic refraction tests were performed, and the data obtained is given below. Determine the slope of the interface of soil layers, depth of soil layers H1, H2, or I have given it is Z dash, Z double dash. So here you can say that will be your Z dash or Z double dash, Z dash and Z double dash. And if you know the beta, you can calculate the H dash, H double dash also. Here H1, H2 means the Z dash, this double dash at point A and B, and the P wave velocity in layers 1 and 2. So these are the data. As I mentioned, so every test, if you interchange the position of the geophone and the source, if it is the horizontal layering case, then they should give the same data, same result. But if it is a layering case, then they will give different data, different result. Okay, you can see here initial part it is same up to 12.4, it is see up to 20 meter. This is the so this is actually it is given, this will be 10, this is 15, this is 20, this is 25, this is 30, this is 35, this is 40. Okay, so the same it is 0, 0, 5, 10, 15, 20, 25, 30, 45, 40. Here also 5, 10, 15, 20, 25, 30, 35, 40, 35. Okay, so same data. So, but if you see up to 20 meter, the values are more or less same, both the cases. But after that, there is a slight deviation. You can see after that there is a slight deviation. So, now that means it is a sloping ground case. Clear? So, now you draw them. So, you can see now this is my first arrival of time, and here you know I have already discussed this will be your TD. This is TD and this axis is TU. Okay, this is TD and this is TU. Now you join, let's join them. So this is first join them. So you can see up to 20 meter or here up to here, there is no problem. Then there is a change. So there also there is a change. Okay, and there if we join them, this is the intersection. This is one case. Similarly, for this case, join them and join them. So here also I will get two curves. So this is TU, this is TD, down, up. Okay. So now from here, the slope will give me 1 by VP1. From here also the slope will give me 1 by VP1. So ideally they should give the same value, but there may be slight deviation, and if there is a slight deviation, then you will get the average of these two VP1. You will get the average of these two VP1. But for my case, it is given from the graph, they are giving the same value. So that's why I can write that VP1 is coming out to be 1600 meter per second. Okay, so X is from here, it is this direction, from here it is this direction. It is written 0, 5, 10, 15, 20, 25, 30, 35, 40. That is for TD versus X. But for TU versus X, again it is 0, then 5, then 10, then 15, 20, 25, 30, 35, 40. Remember that. Okay. So this is 1600. Now if I extend this line, so if I extend this line, then it will be here. If I extend this line, so it will cut here. So this is my T0D, and T0D is coming out to be 14 millisecond into 10 to the power minus 3 second. That I will get from this curve. And if I extend this curve, I will get this. If I extend this curve, this is my TU0. So T or T0U. So if I use T0U, this will be T0U. So T0U, that is equal to coming out to be T0U, this 5 into 10 to the power minus 3 second. Okay. Now if I get the slope, then this will give me MD, and this slope this slope, and this slope will give me mu. Okay, so that means this is, you know, A to B and then C to D. C to D is given mu and A to B slope is given md. So if you draw that md value is coming out to be 1.375 into 10 to the power minus 4 second per meter. So those all these slopes I am getting from this graph. Okay, and mu I will get 3.625 into 10 to the power minus 4 second per meter. So I know that md is equal to sine IC plus beta divided by Vp1, and mu is equal to sine IC minus beta by Vp1. And I know that IC I will get by this expression. These expression I have already derived. Sine inverse Vp1 into md plus sine inverse Vp1 into mu. Okay, now if you put this value, Vp1 is 1600 meter per second and md is 1.375 into 10 to the minus 4 second per meter, then I will get IC will be 24.1 degree. Okay, and beta, you know, the expression is half sine inverse Vp1 md minus sine inverse Vp1 mu. So if I put now this time the value, sine Vp1 is 1600, md is 1.375 into 10 to the power minus 4 minus sine inverse. This is sine inverse. Sine inverse again 1600 into 3.625 into 10 to the power minus 4. Okay, and now I will get the beta value is minus 11.4 degree. So what minus sign indicating? As I have discussed already, that the positive beta means the sloping is towards the positive x, the way I have shown. But the negative beta means the derivation is done with the slope is towards the positive x. So negative beta means the slope is towards the negative x. So that means your sloping ground slope will be like this. So this is beta, which is 11.4 degree. Clear? Towards the negative x slope. So now I have that beta value, IC value, Vp1 value. Now I will calculate what is the Vp2 value. And Vp2, okay, so Vp2 value, you can easily calculate what is the Vp2 value. That you know that sine IC, IC is equal to Vp1 by Vp2. Okay, so Vp2 will be equal to Vp1 by sine IC. So this will be 1600 divided by sine 24.1 degree, and that value you can calculate from here. But now I will show you what is the Z1 and Z2 value. So what is the Z1 and Z2 value, or Z dash value? So Z1 expression, you know, that is half T0U or T0D Vp1 divided by cos IC. So that is Z dash. So this will be half. this is T0D is 14 into 10 to the power minus 3. VP1 is 1600 divided by cos 24.1 degree. So this is giving 12.27 meter. And Z double dash is half into T0U VP1 divided by cos IC. So it will be half into 5 into 10 to the power minus 3 into 1600 divided by cos 24.1 degree. So that is 4.38 meter. So if is ground surface, so this is the slope, and if this is your A point, this is B point, so this is your Z dash is perpendicular one. So this is Z double dash, Z dash. So Z dash is coming out to be 12.27 meter and Z double dash is 4.38 meter, and this is the beta, which is 11.4 degree, and VP1 is 1600 meter per second, and VP2 that you can determine from this equation. Correct? Okay. So this is the so I have solved the two problems for seismic diffraction case. One is for horizontal layering and another is for inclined layering. Now let's discuss about the third case, which is the if the velocity, there is a continuous change in velocity with depth. Third case. Okay. So example, seismic refraction tests are conducted at a site and results are presented here. Find the maximum depth of wave travel corresponding to waves received by receiver placed at 700 meter and 1200 meter from the source. Also determine the K dash. So that means we have to determine the K dash, and the maximum depth the wave is reached. Which wave? That is received by 700 meter geophone and 1200 meter geophone. So that means I have to determine the Z max for the wave which is received by the geophones placed, received by the receiver or the geophone placed at 700 meter and 1200 meter from the source. Okay, so that I have to determine. So let's start. So now what I have done, so here you can see that in the first case, if you see the first case, there is a distinct change of the slope. 3 slopes I can change from the plot, but here you cannot change any distinct you cannot see any distinct change. Okay, so that it indicates that this is the third case where continuous change in velocity with depth. So now here also I will join this point. Okay, and this is arrival time, or basically this is also first arrival time, and distance from the source. So that I have drawn. What I will do now, what is 700 meter and 1200 meter? This is the 100, 200, 300, 400, 5, 6, 700. So here I will take the slope. So this will give me 1 by V 700. Okay, and 7, 800, 900, 1000, 11, 1200. So now this is 0, 100, 200, 3, 4, 5, 6, 7, 8. This is 7. So I am determining here, and I will get the slope here. 7, 8, 9, 10, 11, 12. Another one is here. So here also you will get one slope. So this will give me 1 by V 1200. So in the same way you can get the slope at different location, and the initial at V0 you will get this slope. So this will give me 1 by V0. That is at the initial slope I will get. So V0 I will get from this is 1 by V0. So V0 I will get your from the graph is 500 meter per second. Okay. Similarly, V700 I will get 637 meter per second. Okay. So now what I have to determine? First I have to determine Z max and K dash. So Z max expression, Z max expression and the K dash expression I have already derived. So Z max expression is V0 by K dash into cosec I0 minus 1, and K dash expression is 2 by 2V0 by X total. Total means here 700. So that is the distance between. X total is what? Between the receiver and source, and that is 700 into cot I0. So to determine that I need V0, I need I0. V0 I got, that is the slope 1 by 500, 500 meter per second. Now I0, to get the I0 I know that sine I0 by V0, that is equal to 1 by V max. That is the maximum velocity, which is nothing by 1 by V700. That is the maximum velocity that wave will achieve. Which wave? That is received by the receiver. So I can write that sine I0 will be V0 by Vmax. Here for 700 meter receiver, that means the receiver distance 700 meter from the source, that is V0 by V700. So that is equal to your 500 by 637. So my I0 will be sine inverse 500 by 637. So that is equal to 51.7 degree. So I will get the I0. Now I will get the K dash. K dash will be what? 2. V0 is equal to 500. Now X total is 700. Then cot 51.7 degree. So which is coming out to be 1.13. Now I will get the Z max for 700 meter receiver. So Z max is V0 is 500, K dash is 1.13, then cosec I0 is 51.7 degree minus 1. So this is 121 meter. So that means the wave which is received by the receiver placed at 700 meter from the source will travel a maximum depth of 121 meter from the ground. Yeah. Now come to that second case, that your V1200 case. Now V1200 I will get from here, that slope. This V1200 is 820 meter per second. Definitely, as the receiver distance from the source will increase, the depth of wave, or the depth that wave will reach, maximum depth the wave will reach, that will also increase, and velocity of the wave, maximum velocity of the wave, that will also increase, because your velocity is changing continuously with depth. Okay, so now here I0, because here I0 will be, as I mentioned, I0 is not constant, it depends on the ray or the wave. So that will be sine inverse 500 divided by 820. This is 37.57 degree. So now here also K0 is 2V0 by x total cot I0. So 2V0 is 500, x total here this will be 1200 cot 37.57 degree, that is equal to 1.08, and Z max for 1200 meter receiver, that is equal to 500 1.08 into cosec 37.57 degree minus 1. So this is equal to 296 meter. So K dash, we have two K dash now, 1.13 and 1.08. So the actual K dash will be average of these two. Okay, so actual K dash will be average of these two. Now if you know that actual K dash, then at any depth you can get the velocity at any depth. But why the Z max is required? But Z max give you an idea that how much depth, thus up to how much depth the survey is done. That idea is required. So that will give you by using the geophone data. That means the geophone data that I am using, the receiver data that I am using, how much depth the wave is travel, maximum depth the wave is travel, that information I will get from the Z max value. Otherwise, the velocity you will get if you know the V0, if you know the K dash. Here, if you use the, suppose all geophone data, then you will get say 15 K dash value. Then average of that 15 K dash will give you the K dash. Okay, and that you will put here, V0 is constant. So that will give you the expression of V. Okay, and Z max for every receiver you can calculate. I have shown only two cases, that is a 700 meter receiver and 1200 meter receiver. So I think this is the end of this part. In the next class, I will discuss that I have mentioned that this survey will give you good result if velocity increases with depth. But there may be some case where there will be hidden layer or loose layer or weak layer where this trend will not follow. But most of the cases in the field it will follow this trend, but there may be some cases where this trend will not follow. In that case, you will not get the proper result. So in that case, you have to do some other type of survey, and that I will discuss in the next class. Thank you.